All right, guys. So here's chapter 11. Just a few things before I get started. I still have about 20 of you that have not registered or signed into your mastering course. Y'all need to do that ASAP, because if for some reason I can't come back, which I'm hoping that I can, we may have to test or quiz or something on mastering. And if I'm not there to help you get access, that's on you because you've waited so long. Okay, so I know that I said that it was not mandatory, but it is mandatory in a way, if that makes any sense at all. All right, so chapter 11 is not math intensive. So for some of you, that's good. But it's a lot of going back and remembering how to draw Lewis structures. So if if you haven't done that in a while, or you don't remember how to do that, you're gonna have to refresh your memory in order to kind of get through this chapter. My husband's looking for an animal, but I'm not sure which one he's looking for. Okay. Anyway, so chapter 11 is about liquids and solids and intermolecular forces. So in chapter 10, we talked all about gases. We group solids and liquids together. We call them the condensed state of matter because they're more condensed than gases. And you'll notice my chemistry cat, what my favorite intermolecular force, London dispersion forces. He's cute. All right, so on my slides that I've printed out, it says that these slides are not in order, so I don't know really what that means. Oh, here we go. A big thing that your book preaches on is structure determines property. So if you've not read that in your book, then you've probably never opened your book. Okay, so and it's true, it's very true. We saw that when we talked about Lewis structures and them being polar versus non-polar. Okay, so the composition and the structure determines the type and strength of what is called an intermolecular force. Okay, so intermolecular force is the forces between molecules of itself. So, like, if I'm talking about water, I'm talking about the forces that hold liquid water together, knowing that there are more than just one single water molecule in a glass of water. Okay. So, intermolecular forces are the attractive forces that exist between all molecules and atoms. They're actually the forces that hold your liquid and your solids together. And again, this is why we call them the condensed state or phase of matter. They're more condensed than gases. So your phase of matter actually depends on the magnitude of your intermolecular force between the constituent particles relative to the amount of thermal energy. So all that means is If your thermal energy is high, matter tends to be gaseous because they're constantly moving. And that's what thermal energy really is how fast your particles are moving. When thermal energy is low, matter tends to be in a liquid or a solid phase because your particles aren't moving as fast. Okay. So I think the next few slides talk about the difference between liquids, gases, and solids. You've probably already seen this somewhere along your college career journey. Liquids are closely packed, but they have the ability to move around. Because they are closely packed, they cannot be compressed like a gas can. The ability to move around, though, lets them flow. So that's why liquids flow the way they do. They also take the shape of their container. However, the particles don't have enough freedom or movement that would allow them to escape from or expand to completely fill their container. So they can move, but they're limited in movement. Okay, gases, we just spent a whole chapter talking about. Remember, they're like the gypsies. They're free to do whatever they want, whenever they want. They're constantly moving, constantly hitting each other. They don't stick or remain in contact. They simply bump and go on about their business. Because they expand to fill their container, they are compressible. Let's see. And there's a large amount of space between gas particles compared to the size of the particles. So you can see here's what a liquid look like on the molecular level versus a gas. Okay, solids. Solids are practically immobile. Their particles are packed close together and are in fixed positions. The close packing results in them being incompressible. But it's good to know that they are not completely static in nature. They do move a little bit. It's just they're vibrating in place, or they're stretching out their bonds, okay? So it's kind of more like a vibration more than a movement. So the inability of particles to move around results in your solids retaining their shape and volume when placed in a new container. It prevents them from flowing, so they don't flow like liquids flow. Solids arranged in an orderly geometrical pattern are called crystalline solids. An example is salt, an ionic compound. So for a salt, if this was my crystalline solid down here, it'd be NaCl, NaCl, Cl, Na. They alternate positive, negative. All ionic compounds do that, actually. Or it could be a diamond, which is a molecular structure of just carbon. Particles, solid particles that do not show a regular geometric pattern over a long range are called amorphous solids. Examples of that is plastic and glass, and you can see they're just like a glob over here. All right, so towards the end of this chapter, we'll talk about phase changes between our three states of matter. And what those are called scientifically. But you know that you can change the phase of matter by heating or cooling it. You could also change it by changing the pressure, okay? So we will look at those inner conversions later in this chapter. Okay, so back to intermolecular forces. I will say that this is probably the most boring chapter that we'll cover. Sorry. It's boring to me because there's no math. And I have to talk a lot and I'm congested and my throat hurts. All right, so again, intermolecular forces hold our condensed state of matter together. Condensed state means solids and liquids. These are attractive forces between particles. They are electrostatic in nature. That means that it's really between charged particles. What that means. That's what all attractive forces are, is two oppositely charged particles attracting to one another. The strength of the attraction, again, determines your state of matter. The stronger the attractive force, the higher the boiling point of the liquid, higher the melting point of your solid. What that means is it takes more energy to separate those particles. So you're breaking that intermolecular force in order for them to boil or melt. So boiling a liquid requires adding enough energy to overcome the attraction between all the particles. But when I say we're breaking that attraction, that doesn't mean we're breaking the bond between our molecules, okay? Let me draw an example down here. Let's say this is water. Okay, so these water molecules have an intermolecular force between our negative charged oxygens, our positive charged hydrogens. I'm breaking this attraction in order for me to boil the water, okay? I'm not breaking any hydrogen-oxygen bond, any covalent bond, okay? That is what we call an intramolecular force. Those require a lot more energy to break. So the stronger the attractive force between the particles, the more the particles resist moving. But again, remember that no material completely lacks particle motion. Even solids vibrate and wiggle in place. All right, next slide says, why are molecules attracted to each other? Well, again, an attraction is usually between charged particles. So oppositely charged particles are attracted to one another. So if I have a positive ion and a negative ion or cation to an anion, they are attracted to one another. If I have a polar molecule like water that we were just talking about, the positive pole and the negative pole are going to align so that there's some kind of attraction between them. Even nonpolar molecules will have temporary charges. We call those instantaneous dipoles. Okay, they kind of make their electron density kind of shifts so that they have a temporary dipole in order to cause an attraction. So the larger the charge, the stronger the attraction. Sorry, the longer the distance, the weaker the attraction. Again, it's important to note that intermolecular attractive forces are small relative to bonding forces, which you call intramolecular forces. Because intermolecular forces are smaller charges over a larger distance. All right, so there are actually four types of intermolecular forces. Three of those types, though, we're going to group together, okay? So they are dispersion forces. Sometimes you'll hear these called London forces or London dispersion forces. All molecules have dispersion forces, okay? It's the temporary polarity in a molecule due to uneven electron distribution. So it's where your electron density kind of shifts to make a temporary dipole. So all molecules will do this. So dispersion forces are the weakest forces. And I used this bodybuilding image to kind of help you remember. The next type of intermolecular force is dipole-dipole attractions or forces. This is where you have a polar molecule, and because it has a permanent polarity, it creates a dipole-dipole attraction, like water, okay? So the positive pole aligns with the negative pole on an adjacent molecule, and it kind of attracts one another and holds that substance together. So everybody has London dispersion forces. If you have a polar molecule, not only do you have London dispersion force, but you also have a dipole-dipole force. Okay, then the third and strongest of these three is hydrogen bonding. This is just an especially strong dipole-dipole attraction that happens when hydrogen is attached to an extremely electronegative atom, such as oxygen. Okay, so they're the strongest. So example, water. Water has dispersion forces, dipole-dipole forces, and hydrogen bonding. Hydrogen bonding is the strongest, though, okay? So that's what makes water have such a high boiling point. We're going to look at each of these individually, though. All right, so first we have dispersion forces. Again, everyone has dispersion forces. Everybody. So, sorry. So dispersion forces are just fluctuations in electron distribution within atoms and molecules, resulting in a temporary dipole. So you'll have like a negative charge region, as you can see down here, a positive charge region. So your electrons just shifted this way. So the attractive force caused by these temporary dipoles are called dispersion forces. And you see how they align themselves so that you have positive, negative, positive, negative. So again, you might hear them called London forces or van der Waals forces. As a temporary dipole is established in one molecule, it's kind of like a domino reaction. It induces a dipole in all the surrounding molecules. So again, all molecules and atoms have dispersion forces. So what makes one dispersion force greater than another? Okay, so let's look at some effects or some, what's the word? Some characteristics. I don't know. The first one we're going to look at is the effect of molecular size, right? Yeah. So one example we could use is noble gases. We know that most of the time noble gases don't bond with anybody. There are some exceptions to that, but for the most part, they hang out by themselves. And they are all nonpolar atomic elements. But if you look down here in table 11.3, as the molar mass increases, as you go down the group there, you'll also notice that their boiling point increases. Boiling point, melting point, those are both ways that you would measure intermolecular forces, or they're a way, sorry, I'm having all kind of issues. They're a way that you know intermolecular forces are there, okay? So as you increase your molar mass, you increase your dispersion force, therefore you increase your boiling point. Another way to say that is the second bullet up here. As the molar mass increases, the number of electrons increase. A larger electron cloud is more polarizable, meaning you can shift the electron density more easily. Therefore, the strength of the dispersion forces increase. So anytime you have a stronger attractive force, you're going to have a higher boiling point. Another example over here in this graph is a group of hydrocarbons. So it's just hydrogen and carbon. Hydrocarbons. You see that we start with 5 carbons, 6, 7, 8, 9. So as we add more carbons, we're also adding more hydrogens. So we're increasing its molar mass. And as you increase the molar mass, you're increasing your boiling point. Okay, so if you're looking at something that only has dispersion forces, and you want to know which one has a greater boiling point, then you're going to want to look at their molar masses. Okay, increased molar mass means increased boiling point. Oh my goodness, sorry. Okay. I think he's in there. It's not working. Oh, here we go. All right, something else that affects your strength of your intermolecular force is the molecular shape. So here we're looking at something that's in a straight line and something that's here. They're drawn out for us here. We have pentane, who's in a straight line. Then we have neopentane, weighs the exact same. It's just arranged differently. Okay, so with pentane, there's a larger attraction because two pentane molecules can stack together like this, and you have all this area for attraction. Neopentane, if you stack them together, they only have this little area of attraction. So, pentane, we assume, then would have a higher boiling point because of that, and it does. Okay, so pentane boils at 36.1, neopentane at 9.5. So not only does molar mass, more molar mass means higher boiling point, but also the shape or the structure of the molecule. Okay, so that's dispersion forces. Let's look at dipole-dipole. So polar molecules, and the only way you're going to know if something is a polar molecule is if you were to draw it and you saw that it had a certain geometry. These were our polar geometries bent. Trigonal pyramidal. What was another one? There's three. What have I lost? Bent, trigonal pyramidal. I don't know what I'm missing. Anyway, we'll get there. Okay. So, remember, bond polarity and the molecular geometry determine the polarity. So the separation of charge is referred to a dipole moment. So a lot of times you're going to have to kind of sketch this out in your head to know that it's a polar molecule. All polar molecules have a dipole-dipole attraction, which is stronger than a dispersion attraction. So with your dipole-dipole interactions, it's the exact same as your dispersion, but these are permanent dipoles. Okay, they're not induced. They're permanent. They don't leave. So this attraction right here is a little greater because it's not going to shift one way or the other and then affect your dipole. So, permanent dipole adds to the attractive force between molecules, raising boiling and melting points relative to non-polar molecules of similar size and shape. Okay, so we'll compare down here formaldehyde, who is polar. And it's polar trigonal planar, but this bond is the only polar bond, making it polar. Okay, ethane is non-polar, but you'll notice that their molar masses are very similar. Well, you can expect the boiling point and melting point to be higher for the polar molecule, and it is. It's less negative, so it's higher than you see for ethane. They could have given us something better to look at instead of these negative numbers. But anyway, this is indeed higher than that. Okay. Then hydrogen bonding. Hydrogen bonding is just a type of dipole-dipole. So you have a polar molecule who has a very, very polar bond. That polar bond is hydrogen bonded to a very electronegative atom. These are the only three that we will consider. So if you have a hydrogen-oxygen bond, a nitrogen-hydrogen, or a fluorine-hydrogen, those all have hydrogen bonding. Okay? Because hydrogen has no other electrons, when its electron is pulled away, the nucleus becomes de-shielded. In other words, it's like you have an exposed proton just hanging out. So that exposed proton acts as a very strong center of positive charge, attracting all the electron clouds from neighboring atoms, molecules, sorry. So you go down here and look. Here's your hydrogen. Here's your negative, very electronegative atom. See how they're attracting one another, and they line up so that it's always positive, negative, positive, negative. So it's very much like dipole-dipole. It's just a special type of dipole-dipole. So hydrogen bonds are the strongest that we'll talk about. Intermolecular force, stronger than dipole-dipole or dispersion forces. Substances that hydrogen bond are going to have a higher boiling point and a higher melting point than substances that cannot hydrogen bond. But hydrogen bonds, again, are not nearly as strong as a chemical bond, okay? So I really want y'all to remember that these attractive forces are nothing compared to what a chemical bond is, okay? But it's enough that it affects boiling and melting point. Okay, so if we look at ethanol and dimethyl ether, the formulas you'll notice are the exact same, so their molar mass are the exact same, but the structure is slightly different. I'll draw it out. Well, so you have this carbon with 3 hydrogens. And you have a carbon with 2 hydrogens. And you have an oxygen bound to a hydrogen. So here's my hydrogen bond right there. Then you have this ether. It looks like this. Drew it out. All right. So it has oxygen and it has hydrogen. They're just not bonded together. So this ether doesn't have hydrogen bonding. It is polar, but it doesn't have the hydrogen bonding. So we would expect ethanol, ethanol to have a higher boiling and melting point, and it does. And that is because it has hydrogen bonding, H bonding, whereas this ether is just polar, therefore it's dipole-dipole attraction. Okay, so that's how they would differ. All right. This next slide shows you boiling points of group 6A and group 4A. The biggest thing to note here is water is the only one that has hydrogen bonding, and you'll see that it's boiling point is much higher than everybody else's. Then for nonpolar molecules, like in group 4A here, all they have is dispersion forces. So as you increase your molar mass, you're increasing your boiling point. And then group 6A, these are slightly polar molecules. That's why their boiling points are a little higher than group 4A's. So it's all about trends here and what affects what intermolecular force is compared to another. So this example says one of these liquids is one of these compounds is a liquid at room temperature. Which one and why? This really isn't the best way to ask the question, but what they're really asking is which one has the strongest intermolecular force? I abbreviate intermolecular force IMF. All right, well, let's look. Formaldehyde has a dipole-dipole. This bond right here is polar. This has a dipole-dipole. So this bond right here, but it's not a hydrogen bond. Okay, so it's simply dipole-dipole. This hydrogen peroxide, this is a hydrogen bond, that's a hydrogen bond. So this is your strongest. So we would expect this to be a liquid at room temperature. Okay. All right. I told you in the beginning that there were 4 types of intermolecular forces, but the first 3 we would look at separately. The fourth one is different because you're not talking about molecules of the same type. So when I was talking about dispersion, dipole-dipole, and hydrogen bonding, I was talking about one compound interacting with compounds of itself, like all water molecules, all hydrogen peroxide molecules, etc. Ion dipole forces, that's not the case, okay? It is when you have ions from an ionic compound attracted to dipole of polar molecules. So you have 2 different substances. This is the strongest of the intermolecular forces, but again, I consider it its own category because it's not the same as the other 3, in my opinion. Okay, so a good example is salt or NaCl in water. Well, we know that when salt dissolves in water, it breaks apart into my chlorine ion and my sodium ion. Well, the water is going to orient itself so that on the chlorine ion, my hydrogen molecules are attracted to that negative charge all the way around. The sodium molecules are going to be surrounded by water molecules, but the oxygen is going to be facing them because positive, negative, okay? So that's when you have an ionic compound and usually a dipolar or dipole, we'll say polar solvent. Okay, so that's ion dipole forces. And again, they are very strong, stronger than hydrogen bonding, but I don't see how you can classify them as the same thing. Just my opinion. Okay. All right, the next slide is just a summary of the 4 that we've talked about. So you can read through those. Then I think the next slide kind of shows you just a visual summary and kind of a molecular perspective, and then kind of the strength. So you'll see ion dipole strength is much greater than something like dispersion. This is another good summary. However, if you go to print your PowerPoint for whatever reason, this will not print on the slide. I don't know how to fix that. But this will be beneficial for those of you that go to organic, because it tells you what type of organic molecules have each of these forces, like alcohols, carboxylic acids, amines. Those are all organic compounds. Ketones, esters, alkyl halides, all organic compounds. Those, again, all organic compounds. So you might want to flag this slide if you're going on to organic. All right, so I'm going to stop there for part 1 of chapter 11. And I'll pick up here in part 2. Hope y'all are surviving. See y'all soon.